Hi, and welcome to Data Science for Social Impact. Introduction to R. I'm Raymond, and I will lead you through this course today. We will first begin with a discussion of the RStudio interface. The goal of this course is to introduce you to R in RStudio, which we will be using throughout the course to both learn statistical concepts and analyze real data to come to informed conclusions. A quick clarification. R is the programming language that we will be using, whereas RStudio is the integrated development environment, or the system that we use to communicate to R. As we progress through this course, you are encouraged to explore beyond what we have dictated. Additionally, a willingness to experiment will make you a much better programmer. Before we get to that stage, however, we need to build some basic fluency in R. Today, we will begin with the fundamental building blocks of R in RStudio, discussing the interface, how to read and write in data, and some of the basic commands we can use to interface with both R and RStudio. First, go ahead and launch RStudio. You should see a window that looks like the images shown below. On the lower left panel is where the action happens. This is called the console. On startup, it will display information about the version of R you are running. We can also directly type code into the console to run functions and commands. We can also use it as a calculator. The panel in the upper right contains your environment, as well as a history of the commands that you've previously entered. Any plots that you generate will show up in the lower right-hand corner. This is where you can browse your file, access help documentation, and manage the packages you are using. We will begin with a simple overview of R. R has multiple types of data supported. They range from primitive data frames, lists, tables, arrays, environments, and other things, such as functions, closures, and promises. We will demonstrate some of the simple types and their associated classes. Here, we can see that the first example on line 1, X is assigned to the numeric 1. If we use the class function on the object X, we can see that it prints out numeric. On line 5, we have assigned Y the character string hello world. Once again, when we run the class function on Y, we can see the type of variable that we have saved. In this case, it is a character. Z, likewise, has been assigned the value true. If we apply class to the Z variable, we can see that this is a logical type. We can also change from logical to numeric or integer by using the as.integer function. The basic type unit in R is a vector. Therefore, we can supply R vectors like the examples shown below. We can do it by concatenating a list together using the C and parentheses, or by using the colon 1 to 3, which will generate a list of values from 1 to 3. We can also index these vectors by using square brackets. R provides a lot of convenient functions for data generation. Here are multiple examples of how to generate different vectors of different lengths. Here we can use the rep and seq functions, or replicate and sequence, to generate different vectors. Different inputs will generate different types of values. Read the help documentation to learn more about rep and seq. In order to concatenate values, we can use the C command. Here we have some examples of making a vector and assigning it to the variable X. We can also do some simple math or logical statements using base R. Here we have an example of comparing X is greater than 10. As we can see, R generates values such as true and false, determining whether or not this previous bit of math is true or false. We can also use some other functions, such as which, to select values that are greater than 10. We could also do this by indexing our values with square brackets. Our first example on line 6 shows values that are only greater than 10. Our second example on line 8 shows values that are not greater than 10. We can also use greater than or less than, or combine different operations together using the AND operator. The basis of most programming in R is based off of functions, or collections of scripts or actions chained together to accomplish one goal. We can usually take code and scripts and make functions out of them. Here are some functions that we have generated. Our first function is a square function. We can initialize a function by saying function of the variable of interest, in this case, function of x, and then the body of the function is enclosed within these curly brackets. Here we have defined the function to be x raised to the power of 2. If we run this function on an integer, such as 2, we can see that it returns 4, properly squaring the value. Next, we have defined a power function. This has 2 arguments. Our first value, which is the one we want to raise to a power, and the second value, which is the power we are raising. In the body of the function, we have x raised to the power of p. We can test this out and see different operations using this function. If we only supply the first argument, we see that 10 is raised to the power of 2, the predefined second argument. However, we can specify any integer to the second argument. So if we raise 10 to the power of 3, we can see that the result is 1,000. We can also switch the order of the arguments by defining which value is which. So if we put p is equal to 3 in the first argument, it will know to raise 10 to the power of 3. Functions can also be passed as data, so we can add functions and nest them together to do more complicated actions. Here, we have a function of x and f, where the function x is fed in the function f. So here, we are going to supply g, the first value of 10, and then the second value, or argument, will be a function that we have pre-designed, such as the square function. Here, we can see it will take 10 and square it, as we have already defined the square function. We can list any number of functions and concatenate and nest them together as we wish. R is what is called a vectorized language, which means it will do vectorized math natively. Here's one example of doing vector multiplication by defining a user-made function. Here, we nest a for loop inside of our function to multiply each value at a certain indice by each other, and then return that value. Here, we can see that by applying this function to 2 vectors, both from numbers 1 to 10 and 1 to 10, we can see that we found the squares of these numbers. However, this is a lot of work, and R intrinsically knows how to multiply vectors such that we don't need to define this function. In order to do this the quote-unquote R way, we can take 2 vectors and just multiply them together and get the same value. We would also like you to know that R will recycle values of unequal length, which means that if you have 2 vectors that are not equal, as long as the vectors are divisible by, the length of the vectors are divisible by each other, R will repeat this value over and over again until it reaches the proper length to do vector multiplication or division or subtraction or addition. Here we can see by multiplying the vector 1 to 10 by the vector of 1 to 2, it did the proper multiplication. We can also use R to generate random numbers. R contains a huge number of built-in random number generators for various probability distributions, making many different possibilities very easy. Here, we are using the rnorm function. The first argument of the rnorm function is the number of values you would like to generate. We can also supply the mean and standard deviation of this distribution we want to generate. In our second example, we have generated 10 values with a mean of 100 and a standard deviation of 5. Another important part of R and working with R are called data frames. Data frames are a fundamental structure used in data analysis. It is similar to a database table in spirit. It has distinct named columns and distinct types. In the example below, we have made a simple data frame containing both numerics, character strings, and more character strings. We can print out this table and see that the columns are named X, Y, and Z and have values ranging from 1 to 6 for X, a character string for Y, and 1 and 2 and 1 and 2 and 1 and 2 for Z. As we can see, R automatically knew to recycle the 1 and 2 vector to the proper length for this data table. We can also index data frames. It is also indexed like a vector or a matrix in R. Therefore, if we want the first row, we can take the square brackets, and in row, comma, column designation, we can select the first row by typing in 1. It is important to know that R, unlike some other computer languages, indexes from 1 and not 0. If we want to select the first column, we leave a space in the first entry, a comma, and then write 1, which will select the first column. We can also chain these operations together to select specific rows and columns and different combinations of both. Let's generate some data in a data frame. Here we have written a nice function to generate some random data. We have designed different columns using the time, a character string, and some random number generators. This will simulate something like stock prices over time. If we run this function and supply it the 50, it will generate 50 values for this data frame. We can use the head function to print out the first couple entries from this data frame. In R, we can also add and remove columns on the fly by using the atomic operator, otherwise known as the $sign. We can use the $sign to select any column from a data frame by referencing the column name, such that when we want to select the ask column, we can do prices $ask. We can also do math on these columns, such as the example in line 1, where we subtract prices, the prices column ask, from the prices column bid. We can assign this to a new variable called spread. We can also do more complicated things with these columns, such as adding them together and then multiplying by a value. Here is the result of doing those different operations, and we can see that new columns were generated inside our data frame without having to specify that a new column needed to be named. Here are some basic operations on data frames. We can look at the names of each column by using the names command. We can create a table of a certain column using table and then the $sign atomic operator on a certain column, or we can run the summary function on a specific column or the entire data set. Here are some more examples of using R. Here, we will simulate coin tosses, and we will ask the question, what is the probability of exactly 3 heads and 10 coin tosses on a fair coin? Here are some examples of how we can simulate this. We can use the choose function along with some math. We can use the binomial distribution density function by supplying the probability, the size of numbers that we have, and the number of replicants we want. Or we could simulate 10,000 coin tosses and then sum up the probability. Here we see that these different approaches all converged on a similar value, although the simulation is slightly different than using the binomial identity or the binomial distribution density function. Here, we will once again present a different example using the binomial distribution function, in which we will generate 1,000 up and down movements based off of a fair coin and plot it. This is called a random walk. Writing functions in R is convenient. However, many other people also write functions in R and have publicly uploaded their code for other people to use. It is most of the time more convenient to find code that accomplishes the task that you are trying to do than writing your own functions. And it is highly encouraged to look at different packages and the functions inside these packages to see what they do and how they code. Our packages come from an open source community, which means that users can contribute packages that make our life easier, and we can use them for free. For this course, and many others in the future, we will be using the following R packages: the suite of tidyverse packages, which is actually a collection of packages for data wrangling and data visualization. Also, the OpenIntro package is useful for data and custom functions with the OpenIntro stats books. In order to install a package, if they were already not in your R environment, we can install them by using the following lines of code. In the console of your RStudio session, we can type in install.packages, and then inside of that function, the character string or the title of the function or the package that we would like to install. This needs to be encapsulated in quotes in order to work properly because it takes in a character string and not an object. We can check and see which packages are installed on our system by navigating to the lower right-hand corner of our RStudio pane and clicking on the Packages tab. However, once we download a package, it is not loaded into our RStudio session, and thus we need to library them in order to use them. This is convenient because many packages will have functions that have similar names or the same name, and therefore if we were to load in all of the packages currently available on our device, there would be mass confusion and chaos. When we start writing a script, we always initialize our script by librarying in the packages that we will be using throughout our analysis. In order to do this, we use the library function and then just the name of the package, not in quotes. This is an important distinction between installing packages and librarying packages. When you install a package, you need to encapsulate it inside a character string, whereas when you library a package, you can just type the package name. Also, you will only need to install packages once, but you will need to library them in at the beginning of every single one of your sessions. The tidyverse, as mentioned previously, is a collection of packages that share common philosophy and are designed to work incredibly well together. You can find more about the tidyverse system of packaging at tidyverse.org. In order to make sure that our lab work is reproducible and to save the processes that we are developing, we like to use the R Markdown scripting language to create reproducible lab reports. R Markdown allows us to combine code and text together and knit them together into finished reports. It is a very nice way of using RStudio, and in fact, this entire presentation was made in R Markdown. Thus, we can not only create good code, but also wrap it up into a really nice product. The following links will give you some more information on why we should use R Markdown for lab reports. As mentioned, R Markdown is the scripting language, or the way of processing our R code that we like to use. Going forward, we would like you to refrain from typing code directly into your console unless you are debugging. This allows us to have a record of the types of functions and processes you are using to analyze your data. We can also run these chunks or bits of code at once at a time, much like a Jupyter notebook. We can run these functions by clicking on the little arrow function at the top of a code block. We can also highlight the code and use Control-Enter to run the code. At any point, if you need to start over, you can run all the chunks above where you're currently at by using the arrow. Here are some additional resources for working with R and RStudio. We highly recommend you look at the book R for Data Science by Grohman and Wickman. This is a complete overview of using tidyverse and developing yourself as a data scientist in R. It is a fantastic resource and provides in-depth knowledge for using tidyverse functions along with many demos and interactive coding. Additionally, if you want to look for online help and are Googling for R code, make sure to include the package that you are specifically using and the types of problems that you are trying to solve. For example, Googling scatterplot in R is not very useful because there are thousands of ways of making a scatterplot. However, If you are specifically looking for help of making a scatterplot using the tidyverse, you should be searching for scatterplot in R with the tidyverse. This will provide you with a lot more in-depth information and specific code chunks on how to use it. Finally, there are many cheat sheets made by other users of R that will come in handy. Here are some examples below.